Okay, so yesterday I mentioned that really today and yesterday's notes are really one big lesson. I've just broken them up into two different pieces. So I called one of them the remainder theorem and one of them the factor theorem, but honestly I've kind of been working with both at the same time anyways. So let's do a quick recap of what we learned yesterday. I would say there are three main skills you learned. The first one is we talked about how to do division, and often we ignore how to divide. Because I pointed out, like on your calculator, if I ask you to do 8 divided by 3, you get 2.6 repeating, and once you guys got past a certain point, you just use 2.6 repeating. But it might be better for you to recognize that that is actually 2 2/3. And the reason why it's 2 2/3 is because, yeah, 8 divides by 3 evenly with 2 left over, but there's a remainder of 2. And if you were to take like the 0.6, the repeating portion, and turn it into a fraction, if it turns into a fraction, apparently that one won't, then 2/3 means that there's 2 out of 3 cookies left over. I don't know if you like to divide things amongst people with cookies. So that was one thing we talked about. Second thing we talked about was how to do either long or synthetic division, where you do this whole process where you take your x minus 1 and you do your long division bit here. Right? That's one skill. But then there's also that synthetic division, which is where I made like a grid out of it. But really, all of that pales in comparison to the actual theorem we learned, which was the remainder theorem. The idea being that if we just plug in a number, the opposite value of that number is kind of helpful. So today I want to start by talking about vocabulary. So we're using the right words. Okay. Let's say I give you a polynomial and it's written in a factored form. Like for example, if I give you x minus 2, x plus 1, x minus 3. That's not factored form, right? The factors are x minus 2, x plus 1, x minus 3. Those are the factors. And ultimately, if that's our goal, that's done. But the roots of this are going to be just these numbers on their own. So like the root of this one is 2, the root of this one is -1, and the root of this one is 3. You guys are comfortable with that? The idea then behind the remainder theorem is, if you were to just plug in the root into the equation, it will tell you what the remainder is. Now, if there's a remainder, do they divide evenly? No. And so if we're looking to factor, we need them to divide evenly. So if there is a remainder, it's no good. If the remainder is 0, then it is a factor. And that's basically where we want to start today. Just the idea of how to use that to solve a bigger problem. Because ultimately our goal, if I can fast forward here, is going to be to take something like this, and I want to be able to factor it into say x plus 1, x minus 2, x plus 4, x plus 3, whatever that happens to be. That's what we want to be able to do. And we need to use all of these sorts of rules we've learned along the way to get there. So far, so good? Flip to this slide here, then. Can you guys find this one here? I know I'm kind of going out of order. I think we're ready for this, though. So, the remainder theorem. Okay, this is the mathy jargon to it. Let's put it into people words. Okay, so into people words. The remainder theorem basically says that if you use a root, not a factor, but if you use a root and plug it in to the equation, it will tell you the remainder. So hypothetically, let's say the factor is x minus 3. What number should you plug in?
Mr. Cleaver, can you please call 3500?
If you plug in 3, it will tell you the remainder. That's the remainder theorem. But that's not usually useful to us. We need to specifically seek out things where the remainder is 0. So if the remainder theorem basically just says plug a number in, it tells you the remainder. Okay? The factor theorem goes a little step further, and it basically says that this thing right here is a factor if it equals 0. So if the remainder is 0, then it's a factor. Does that make sense? Remainder theorem, plug in a number, it'll tell you the remainder. Factor theorem, plug in the number. If it's 0, then that number is the root. And if you flip the value around, like 3 to -3, then that's your factor. Sound good? So let's try some examples. Let's go back and do this one here. So I know it's out of order, but let's try this one though. Let's find some of the roots of this function. First question, how many roots could there be up to? Up to 3. Why? Because it's cubic. Makes sense? Does there have to be 3 roots though? Let's talk about what a cubic function looks like from a graph. As a graph, a cubic function could look like this and have 3 very distinct roots. That's possible. The cubic function could look like this, where there might only be 1 binomial you can find. And then the last little bit would be like a quadratic that can't be factored. It's even possible to have one that looks like this, where like there's 1 right here, and there's just 1 right there, and it touches. So those are some of our possibilities we're looking at. So in order to figure out whether something is a root, let's use that remainder theorem. Let's just pick a number. 1. Plug in the number 1. So I'm just going to write it out like this. F of 1. So 1 to the 3 minus 3, 1 squared minus 1 plus 3. And I'm just going to see what it equals. This is going to equal the remainder. So 1 minus 3 minus 1 plus 3 actually equals 0. What does that mean? This means x minus 1 is a factor. That makes sense? Let's pick another number. Let's just do it sequentially. Let's do 2. So let's go f of 2. That'll be 2 to the 3 minus 3, 2 squared minus 2 plus 3. And let's see what that equals. This is the remainder thing. So that'll be 8 minus 12 minus 2 plus 3. Minus 4 minus 6. I got minus 3 when I'm done. Do you guys get that? What does this mean then? This means x minus 2 is not a factor. Okay. I think I said yesterday that sometimes this process is frustrating because it's not necessarily hard work, it's tedious. Because we're going to have to keep testing, right? I have now found one thing that I know is a factor, but I found one that I know is not a factor, so let's try another one. Let's try f of 3. 3 to the 3 minus 3, 3 squared minus 3 plus 3 equals, what is our remainder? That's 27. That's actually 27. That's 3, that's 3. And 0. So according to the remainder theorem, I have now found the remainder when we were to long divide this. If we tried to long divide this, the remainder is 0. As an offshoot of the remainder theorem, if it does equal 0, then it means it is a factor. You guys get that terminology there? Remainder theorem, big picture. Factor theorem, like a little subset. If it's 0, then it's a factor. If it's any number but 0, we just go, meh. Like, does the fact that this is minus 3, does that mean anything to us? No. Alright, if it was minus 4 or minus a million or minus 7, who cares? Because if it's not 0, it's no good to us. You know what I'm saying? Okay. So I found 2 of them right now. If I were to factor this thing, I'm going to write it above here. One of the factors should be x minus 1. Another one of the factors, I'm not going to write it out again if that's okay. But if I were to write it out, this means that x minus 3 is another factor. There's got to be one more, right? So, now I've only been working with positive numbers, but negatives are possible, right? So let's try some negative numbers. Why don't we try f of negative 1? Negative 1 cubed minus 3, negative 1 squared minus negative 1 plus 3. Not that brackets there. Negative 1 cubed is negative 1. Negative 1 squared is 1 times by negative 3 is minus 3. Then you're adding 1 and adding 3. Okay, what do you know? It's equal to 0. So if I were to write out a statement here, just so you guys are clear on how this works, we just used the remainder theorem. We plugged in a possible factor. No, we plugged in a root, a possible root, to see whether or not it would work. The remainder theorem gave us 0, so it's actually not just the remainder theorem. It is actually, we actually use the factor theorem, which says that if minus 1 is my root, it means that x plus 1 is my factor. If you wanted to, I'm not going to recommend we do it, but if you wanted to, you could foil the crap out of this thing, and hopefully you'd get that thing right there, but let's not foil all of it. Let's just use a little bit of common sense. X times x times x. I'll give you x to the 3, right? Which is good. That's what I'm expecting. And then maybe let's use the last numbers. Minus 1 times minus 3, that would give you plus 3. And if you eventually times that plus 3 by plus 1, wouldn't that still give you plus 3? Now, this isn't a guarantee that we did it right, but this is a quick little, like, I'm just double checking surface level. It looks like we're doing it. So there, we're factored. Here, come back
Can I
later.
ask you a quick question?
Yeah, come on.
Can you press pause for that?
I can press pause.
So, and
Alright, you guys good with this so far? Okay. I skipped this slide, but this just talks about roots versus factors. I'm going to beat that to death enough. Do you guys get the idea? Okay. I should point out that this is now in addition to your other main factoring skills. So you cannot forget how to do just other factoring, right? Like if I were to give you, for example, a quadratic of x squared plus 6x plus 5, do you guys feel like you're still fairly fluent in knowing that this is going to be x plus 1, x plus 5? Like, you remember how to do that from previous years? You can't forget that, because that could still be useful to you. So I threw a slide on here talking about some of the main types of factors that you may be asked to do. I wasn't planning on going through them, but I'll just say on a one-off basis, if you are like, oh my goodness, I don't remember how to do like this one right here, can we talk later? So basically, you now have a fifth skill. You can use any of these methods right here, or you can now use the factor theorem. That's kind of like your next option. And these are all good for linear, quadratic kind of stuff. This stuff is now good. It's actually still good for linears and quadratics, but it's now good for like cubics, and quartics, and quintics. And then the last thing I got to point out here is that even if you can't factor, if the question just wants you to solve for roots, you can use the quadratic formula, because quadratic formula will tell you what x equals. Now, it won't find you what the factors are. Like it won't, like let's say the factors are supposed to be 5x plus 7 or something like that. If that's what I'm asking you to solve, that won't work. But if you just need to know that x is going to be 2 plus root 7 over 8, something like that, quadratic formula can at least do that part. So let's try another example here. Let's find the roots for this function right here. So let's just do the exact same thing we just did. Let's start guessing and checking some values. So I don't see any reason not to start at the beginning with 1. F of 1. 1 to the 3 plus 2 times 1 squared minus 5 times 1 minus 6. And at some point here when I do this, I just either put a check mark or an X as to whether it equals 0 or doesn't. Like if it doesn't equal 0, I move on immediately. Right? I don't. So like this is 1 plus 2, that's 3 minus 5 minus 6, that's not 0. Moving on. I don't care what the number is, I know it's not 0. You know what I mean? So faster. 2. 2 to the 3 plus 2 squared minus 5, 2 minus 6. That's 8 plus another 8 is 16. Minus 10 minus 6, that one works. There's 1. How many am I expecting? Okay, but I want to show you a different idea this time around. Because you know what we were doing in the past years? We were just kind of flailing away. I was just randomly guessing away at stuff, right? And you hopefully would agree with me that like that is not necessarily the most efficient method to just test 1, 2, 3, 4, 5, 6, 7, -1, -2. Like that's ridiculous, right? That's not the most efficient way. So I'm going to combine some of the skills we've learned now. Now that I know that 2 works, it means that x minus 2 is one of my factors. I'm going to do synthetic division now. Watch this. Using synthetic division, this is where I'm going to write like -2 and like my my grid like this. We doing this last day. I'm going to write out the coefficients then of the original polynomial. So the original coefficients are 1x to the 3, 2x squareds, minus 5x, and minus 6. What's the first step? You guys remember what to do on synthetic division? Drag down the 1. Minus 2 times 1 is minus 2. Subtract. Now it's double subtract because it's going to be subtract the negative, so it makes it 4. Minus 2 times 4 gives you minus 8. Double subtract is going to mean to add, so minus 5 going back up 8 will give you 3. Minus 2 times 3 gives you minus 6. At this point, I'm breathing easy because the minus 6's are the same as each other, so when you subtract them, it gives you a 0. So this does a couple things. Right off the bat, it confirms that x minus 2 actually does work, because this last number was the remainder. So far, so good? But here's where this is useful putting it all together. This is your constant term, that's your x, and that's your x squared. Really, what I've done is I've knocked out an x minus 2, and this whole cubic thing right now can be written as x minus 2, and then the remaining portion is the x squared plus 4x plus 3. Well, this is where just good old-fashioned grade 10 factoring comes in. X squared plus 4x plus 3. Should be able to do that, right? This guy is x plus 3, x plus 1. Wasn't that a lot faster, or maybe at least efficient, than just randomly guessing and checking? Right? Because if I randomly guessed and checked, I mean, here's what I probably would have done. I would have checked 1, I would have checked 2, I would have checked 3, I would have checked 4, I would have checked 5, I would have checked 6. After a while, I would have been like, this is getting dumb. And then I'd start checking the negatives. Then I might have checked -1. Well, -1 would have got me this one. -2 wouldn't have worked. -3 would have finally got me this one. I might have checked like 6 or 7 different one of these ones to get there. Isn't that kind of ridiculous to check that many? So as soon as you find one, a good strategy is use synthetic division. Use synthetic division, knock out a single binomial over here that you divided by. It'll give you a quadratic left over, and then just factor the quadratic. That makes sense? There's actually a theorem behind this. There's a third theorem, so we're doing 3 theories today. Remainder theorem basically says plug in a number. If the number gets plugged in, that'll tell you what the remainder is. Factor theorem is, say you're plugging in that number. If the remainder is 0, it's a root. This last theorem is called the integral 0 theorem. And again, I gave you like the technical jargon. Let me put it into people words, and I'm going to go back a slide here. What it really says to do is focus on the constant term. Okay? This constant term, remember how like when I did my quick double check right here? This constant term is really made up of -2 times by +3 times by 1, right? Because isn't -2 times 3 minus 6 times that by 1 going to give you that -6 right there? Essentially what this theorem on the next page says is that the only possible roots are going to be things that are factors of this last number here. There's no point in trying 5. Because what is 5 going to times by to get 6? Well, not a whole number at least. You understand? So the idea basically is there's not even any point in trying any numbers except for the numbers that are factors of the last number. Like, don't bother trying 8. Because there's no way that if this was 8 right here, wouldn't 2 times 3 times 8, wouldn't that make this constant term way too large? Right? So that's kind of what this theorem says in like fancy words, is if it's a factor, then it's a factor of the constant term. Let me show you how to put this into practice with our next example here. So here's our next example. We're going to try now long divide this, or synthetically divide it, or factor theorem. I don't care how we solve this, but we need to break this up so that by the time we're done, I'm expecting probably 3 of these guys here. But right off the bat, I actually know something useful based on this 3 right here. I know what my outside numbers right here are going to be. It can't be 7. That's not reasonable, right? Because it can't be 7 and that one 1 and that one 2, because 7 times 1 times 2 is not going to get you 3. You know what I mean? Now, I don't know what combination they're going to be or what plus minus they're going to be, but like, this could be 3, this could be 1, this could be 1. It could be something like that, right? This could be a plus 3, and a plus 1. That's possible. It could be that it's a minus 3, a minus 1, and a plus 1. Does that make sense? So I don't know what combination there is, but at least right off the bat, I have some idea of what to guess. So I'm not just flailing in the dark going, I don't know, let's try 6, 5, 4, 3, right? So based on this logic, here's what this dictates to us. Only try plus 1, minus 1, plus 3, and minus 3, because those are the only factors of 3. You know what I'm saying? Don't bother trying 2, because 2 can't multiply by a whole number to give 3. So let's start where we did last example. Let's pick some of these numbers. Let's try 1. That'll give me 2 minus 5 minus 4 plus 3. That's minus 9. That's plus 5. That is not going to work. All right, so 1's out. All right, so let's pick another number. Let's try negative 1. By the way, one quick thought. I'm blitzing through this math in my head here. I'd really like to suggest to you guys, try not to rely on your calculator. Like, yes, you have it. Yes, you can use it. But try to build those mental math skills. Because if you're constantly relying on that calculator to do something like this, then it's slowing you down, probably. I mean, maybe it's not. Maybe this really is a struggle. But this is something you need to work on. Then. This will give you minus 2. That'll give you a plus 1, but times by minus 5 is still minus 5. That'll give you a plus 4. That'll give you a plus 3. Oh, it does work. So what have we learned at this point here then? What is a factor of this thing up here? Not x, subtract 1. That's the key. Make sure you get your pluses and minuses straight. So I'm really going to hammer in the wording. We have found a root to be minus 1, which means a factor is x plus 1. So I'm just going to write that up here. I know that one of my factors is x plus 1. Okay, now I can keep flailing away in the dark trying to figure out where some of my other factors happen to be. Or, a better idea, let's use the synthetic division thing now. So for synthetic division, you use the factor. I'm going to do x plus 1 into my grid kind of concept here. And the coefficients are 2, minus 5, minus 4, and 3. One of the reasons I like using this method, by the way, is that you know when you're right. Because if you don't get 0 as the bottom number in the column there, if you don't get a 0 there, then you know you did something wrong. Okay, so step 1, drop down the 2. Essentially you're doing 2 minus 0, because there's nothing there to begin with. 2 times 2 is 2. 5 subtract 2 gives you minus 7. Multiply the minus 7. Minus 4 subtract minus 7 means to add, so you're actually going up 7 to 3. This is good news. 1 times 3 is 3, which gives you our 0, which I was expecting. Okay, so it means that if I wanted to write this out now, it's actually x plus 1, and the quadratic is 2x squared minus 7x plus 3. We should be able to factor this guy. One of the more challenging methods. Do you guys remember how to factor one that has the number in front? Okay, so add to give the middle, and then multiply to give not just the last one, but the last one times the first one, which will be 6. 6 and 1 both negative? Yeah, that'll do. Okay, now let me show you what not to do here. Don't make it x plus 1, x plus 6, x minus 7. That's not it. Because doesn't that just already break one of the rules we had where like this 1 by the 6 by the 7? But that's not right, right? So, because one of the twists about this one here, if I can go back up to the top here, one of these factors up here is going to need to have like a 2x in it. Does that make sense? Right? I don't know whether it's going to be the 2x with like a 3 or a 2x with a 1, but somebody up here is going to have to be like a 2x something in order for this to work. So we need to use like the longer method here, where we go 2x squared, let's go minus 6x minus 1x plus 3, cut it in half. You guys remember doing this? Factor out of 2x, x minus 3, factor out of minus 1, x minus 3. Okay, I'm not stuck there. All right, final answer. I have 3 roots. One of them I figured out a long time ago was x plus 1. I knew that because when I plugged in minus 1, it worked. Another factor is going to be x minus 3. If I'd have gotten around to plugging in 3, it should have equaled 0. I didn't get that far. The final. Okay, so I'm caught back up here. Has anybody found a factor that made it equal 0? What have you guys tried so far? Like, what numbers have you plugged in so we can cross them off the list? 1 doesn't work, so I'll just make a list up here in the corner. So 1 didn't work. Anybody tried 2 yet? 2 doesn't work. 3. All right, well, let's start trying some negatives. Try -1, -2, -3. See where that goes. I would say this is probably complex enough that it probably wouldn't hurt to use your graphic calculator on this one because it's probably faster than doing it in your head. So, do you guys know how to use your graphic calculator and like go back up a row and like just replace the number? Because that would be an efficient way of doing this one. Like if you did like say -1 to the power of 4 minus 5, -1 to the power of 3 plus 2, -1 squared plus 20, -1 minus 24. Ah, that didn't work. Okay, so -1's out. If you press second entry, or if you got a fancy calculator, you can just go back up. You just change the number out. Turn it to 2, to 2, to 2, to 2. I got one. So I know -2 works. You found one that works there? You said +3 works? Okay, well, we just need to pick one of them that works now. So let's hold on to +3 for later. We'll use that one in a second. Let's start with -2. So if -2 works, then my factor is x plus 2. Let's do some synthetic division using this kind of chart thing here. So 1, -5, 2, 20, and minus 24. Your coefficients. I'll just start doing it. Let me know if you got lost. I'm in mistake. Oh, I put that at 2. Yes. Alright, I think I finally got it. I think I made 2 mistakes along the way. I got 1, -7, 16, and -12 as my remaining numbers. You guys able to replicate that on your own? Okay, so let's work backwards. The 0 is the remainder, which is good. It proves that we did it right. 12 is your constant term. 16 will be your x term. -7 will be your x squared term. And 1 will be your x cubed term. So we managed to pick one factor off. If I wanted to, I can now write this as x plus 2 next to the x to the 3 minus 7x squared plus 16x minus 12. So far, so good. The problem is that this x cubed thing here, there's probably still more that can come out of that one. Now, when we were guessing and checking random numbers at first, I found a -2 worked. Jessica, you said 3 worked, correct? Okay. So why don't we now try 3? But let's not do 3 into what's currently here. What we want to do is take this cubic thing here, and let's pick a 3 out of that. Does that make sense? So when I do my next synthetic division, let's do x plus 3, and let's try to pick an x plus 3 out of a 1, -7, 16, and -12. You know what I'm saying there? Don't go back to the top equation. Rip this out of the cubic equation. The 1, the 3, that's -10, 30, 40, 6. What was that? Oh, because you said that 3 worked.
Yeah.
Oh, that's not me, guys. It's supposed to be x minus 3 because you said the root was 3. I think that's my fault. I think you said it properly and I just didn't listen to you. This is a good learning point though. If you were doing what I was doing there and you're like, hang on, this isn't equaling to 0 over there, you know you're making a mistake. So double check to make sure you don't get your root and your factor backwards. Because the root is 3, so the factor is x minus 3. Big difference. Good learning moment though. Okay, let's try this again. That's a -3. This one's -3. And this -4. 12 over 4. There we go. Let me know if you don't get to this by the time you're done. Any issues with that? Okay, so put this all together now. Here's what we have. As a running tally, one of our factors was x minus 2. One of our factors was x plus 3. The remaining bit is x squared minus 4x plus 4. Is that correct? You guys have a same thing now? Oh, hang on. Where am I wrong?
The second factor should be x.
Oh, it's x. This was an x plus 2. Shoot. And that was x minus 3. I am doing bad here. Okay. Now are we in agreement? Okay, so this was the factor that came from testing -2. Yeah. This is the factor that came from testing positive 3, and now this is what we have left over. At this point here, we should just be able to factor this as a quadratic. Yeah, this should just be x minus 2, x minus 2. So our final answer is x plus 2, x minus 3, x minus 2, x minus 2. Now, there is no way in the world that I would expect you to refoil that out. Because honestly, that's going to take you 10 minutes. But we should be able to do a cursory check to make sure that it makes sense. Like, x times x times x times x is going to give you an x to the 4. That makes sense? If there was like a 3x to the 4 at the front there, I'd expect one of these guys to have a 3. For the last step, if you do 2 times minus 3, that's minus 6, times minus 6 by minus 2, it's plus 12, times 12 by minus 2, you should get your 24 there. That's pretty good. Okay, one last thought then. How many roots do we have? How many roots do we have? Jamie, you have it right. We only have 3. Okay, key terminology here. We have 4 factors. We have 3 roots. You know what this does to the graph? Okay. This is going to give you a root at minus 2. I'll put it right about there. This is going to give you a root at 3. I'll put that about over here. This is going to give you a root at 2. But whatever happens when you have 2 of them right here, this is where it like just barely touches and just turns around right on the axis. So this is a graph that I'm expecting to do this. It's just going to barely touch right there before coming back again. Does that make sense? It has 1, 2, 3 roots, but it does like a double touch right there. Do I have a name for that? I have it in future notes, but we may as well talk about it right now. This is called a multiple root, or sometimes we use the word multiplicity. It just means that you have the same root more than once. So you have 4 roots, but you only have 3 distinct roots, if that makes sense. So there's only actually, you have 4 factors, but the 4 factors only gives you 3 roots. Does that make sense? Okay. One more what if type scenario. You know how we got down right here to this quadratic right here? Hypothetically, let's say that it actually gave you x squared minus 4x plus 17 million. I'm just pulling a big number up for no reason, right? And let's say that it could not be factored. What it could mean then is that the graph would look like this. It could mean that you have one root over here, you have another root over here, but the other bit can't be factored. It might cause it to look something like this. See how like, here's one root, here's the other root. Here's where the graph was trying to come up and provide either 2 more roots or 1 more root, but because it was unfactorable, it kind of just goes only that high. You know what I'm saying there? That's also possible. So it's entirely a reasonable thing where if it's the power of 4, you might be able to knock off 2 factors, and the remaining bit might be something that just gets stuck there. Does that make sense what I'm saying? Okay. I'm going to do these last slides and I'll let you guys finish the last one here. So here's kind of my pictures to illustrate what's happening here. It's possible that you could have 1 root where it only goes like this, and maybe it doesn't quite go low enough right here. Let me make up a possible example of what this would look like. This could be x minus 1, and then x squared plus 4x plus 7. Right? Where the x minus 1, it provided that root right there. You know what I'm saying there? But the x squared plus 4x plus 7, see how that cannot be factored? Because it cannot be factored, that guy right there wasn't able to go low enough to get us such an answer. This one right here could be x minus 1, and then it could be x minus 4, and a second x minus 4. See how the x minus 1 right here provides you that root right there? And see how it just like barely touches right there? That's because this is known as a multiple factor. It factors to the 2 factors, but it only provides just the 1 root. It just touches. And then the final possibility, this is the most normal one. This might be x minus 1, x minus 2, x minus 3, where there are actually 3 different ones. You know what I'm saying? So don't be surprised then if you have a scenario where everything factors out uniquely, everything factors out, but you have something more than once, or only part of it factors and the remaining bit is just stuck there. And I feel like that's probably what my last slide here kind of shows as well, is even though it's to the power of 4 or something like that, it may not actually factor entirely, or even 4 or 6. Okay, let's try this last example then. Why don't I have you guys do this one first with a lot of lead time, so I'm going to let you guys do it without me kind of jumping in. See what you can do. this though. And when we do this right here, this is negative mu squared, so, which then proves that it can't be factored. Because I'm looking back at this right here, like range go 3 today, 1, 2, 6, 7, 7. That's not going to be 3, right? So I know there's 7. So it means that it's this, that, and that's the sergeant. I tried something new. I've never done this before. I froze the screen, but I still did some work on there. Have you guys had a chance to give this an attempt? Do another second before I throw this up here? Okay. Because then all of a sudden the screen's just going to go, there's lots of stuff up there. I've never tried this before. So. Okay, so here's what I did. I started by trying number 1 because it just seemed like the most logical, and hopefully you can see here. I'll use my pencil to follow along. I tried the number 1 up here. 1 worked, which was great. I mean, first time, that's awesome. You feel good when you get it the first time, right? It equaled 0, so therefore x minus 1 went over here. I did my synthetic division. It ended up giving me a 0 again right here. Good news, things are going well. It means that I get x minus 1 as one of my factors. I picked it out of the cubic, and I'm left with x squared minus x plus 3 left over here. And then I said, well, let's try to factor that. And I looked for numbers that tried to add to give 1 and times to give negative 3. I thought, well, I can't do that. But I just wanted to be sure that I was done. So I actually used the quadratic formula, which is what I have kind of sitting down here. But if you use the quadratic formula, I actually get a negative under the square root sign, which is good, actually. I mean, normally we didn't like that last year. It was frustrating. But here this actually makes sense because now it just confirms for me that this guy right here can't be factored. So this right here was your final answer. And if you get that far and recognize that is where you stop, that you didn't need to go further. I mean, if I wanted to, I could just do a quick cursory check. X times x squared will give me the x third I want. Negative 1 times by 3 will give me the negative 3 I want. I'm sure everything else will FOIL out properly. So this right here is as good as I can get. I can FOIL it into a binomial and a trinomial, but this trinomial here is done. Wait, last thought. Let's talk about what this would look like as a graph. I don't want to use my calculator yet, but I will to confirm it. This is a cubic graph. What do cubic graphs usually look like? Well, they usually have like that sort of weave sort of shape to it. Right? However, it won't look quite like this because of the fact that I'm only going to have 1 root. I'm going to have a root over here at 1. I'm going to have that much. I know it's going to go like from this quadrant across the map like this. And it's going to have like some sort of little turn that doesn't actually take you back across the axis. And so what I did over here is I graphed this thing for you so you can take a look. Here's what that graph looked like. Do you see how right there's your intercept there at 1, which we expected. But it just has kind of like a little wave in it. It doesn't actually it didn't even do like a full turnaround. It just kind of did like a little and then kept going. The reason why I did that is because of the fact that this quadratic right here was unsolvable. If it hadn't, it would have done a full-on turn, and you might have actually had your 3 roots to it. So, you see how this kind of comes full picture now? So for our first section here, we're kind of done the first half of the unit. There's 2 main parts to what we've talked about. No, three main parts to what we've talked about. The first one is topic 1. Do you know how to basically graph linear, quadratic, cubic, quartic, quintic? Do you know what the graphs are going to look like in terms of a rough shape? Then for a brief while, we kind of went away from that, and we talked about how to add, subtract, multiply, and divide graphs from each other, plus put one graph inside the other graph using that like G bracket X notation type stuff. Does that make sense? The reason why I did that, though, was to really focus on division, because division is very useful for factoring, which is the last topic we've talked about, is when you have these cubics, quartics, quintics, quadratic stuff, you know how to factor them. And essentially, factoring is dividing. Only if it factors, there is no remainder. That's the real key to it. If it's going to factor, there is no remainder left over. So putting all of this stuff together Can you graph stuff? Can you factor stuff? And if need be, can you add, subtract, multiply, divide, and do composite functions and put them together? That's kind of our first section. Does that make sense? Okay, we got about 20 minutes left today. Monday, I'm going to give you guys some work time, and Tuesday, we're going to do a quiz. Just so you guys know about how I'm going to structure the unit, I'm going to make your first couple quizzes written response quizzes, just because it lends itself better at first to doing a little more written work. I'm always going to make your last quiz, though, before a unit test multiple choice, and your unit test will be multiple choice as well. Okay, so I'll always make sure I give you at least one multiple choice, one to practice. But our first couple quizzes are going to be written ones. It fits what we're doing better, because sometimes you just have to show your work and practice those written skills. You know what I'm saying? So, okay, last thing, and then you guys can take off if you want, or keep working if you want. We have a new assignment if you haven't started looking into that one yet. Most of you guys have talked to marked your assignment now, right? Because you guys are working on it. You guys already did that. Have you marked yours yet? You guys did. Did you mark your assignment yet?
I need to.
You need to. Okay, so maybe do that sometime today. The new assignment, though, is up here. I'll just find it for you. Have any of you printed it off already yet? Okay, maybe I'll print some for you right now while I'm on the site anyways.
Just for good, I'm marking it.
We have something on.
Slow internet today.
What are we doing?
Oh, I didn't post the assignment number 2 yet. Oh my goodness, I am such a bad teacher. Here I'm wondering why you didn't print them yet. Okay, let me just print them for you guys in a second here. Why don't I find it in my notes here for you? Okay, here's what the assignment's going to look like. Let's just talk about some of the questions. No wonder you guys couldn't start it. Okay, so here's what it'll look like. The first question is, I want you guys to factor those things. So the first one you can see is a cubic. You're probably expecting 3 roots, right? And then the next one is a quartic, so you're expecting 4 roots. Okay. Second question, I want you guys to show me that you know how to use long division, synthetic division, and remainder theorem. Okay. Either way, you should get the same answer when you're done. When you do long division, when you're done, it gives you either it works out perfectly or you have a remainder left over, right? When you do synthetic division, either it works out perfectly or you have a remainder left over. And when you use the remainder theorem, for example, when you have this one where it's x minus 2, when you have x minus 2, what do you plug in? Plus 2. There you go. Okay. This one right here is kind of a mix then of what we've been working on. Here I'm asking you to literally plug in the number 2 into this equation. But here I'm asking you to plug the number 1/2 into this equation and into this equation. And then when you're done, add them. Does that make sense? And I'm throwing a few more twists at you here. Here I'm asking for you to throw in like root 2. Can you deal with it if there's a root on it? It's just an extra little twist. Okay, one more thing I haven't talked about. I should have pointed this out. If I want you to solve something like this, how do we solve quadratics? What's like the first thing you have to do when you use the quadratic formula? You have to make one side equal to 0. Okay, so if I give you something like this, if it's not equal to 0, just bring it to the other side and make it equal to 0. Because you're solving for when it's equal to 0. But the other thing I didn't point out is you can solve this graphically. You guys know what I mean when I say solve it graphically? Type in this as y1. Type in this as y2, and you're going to get some sort of graph and some sort of graph. Where they intersect, match your solutions as well. Does that make sense what I'm saying there? So when I ask you to solve this one here algebraically, do what we've been doing all along. When I ask you to solve it graphically, graph this, find where they intersect. Okay, anyways, I'll print this off for you guys, and then you can get started on it. And then if you guys do want to take off, because I know it's kind of the end of the day here, so long as I've got your assignment marked, just sign the board and the thing there. So, but I'll print this off for anybody who needs one.
what is it?